Okay, in the last video, we looked at differentiating exponential functions. However, I cleverly avoided problems such as the ones you see in this page. We only looked at derivative of e to the x. So what if, there's more than just x up there? Well, what it requires is chain rule. And again, I'm not going to elaborate on why this is true. Let's look at just how to use it in this video. But I use this because it flows. The derivative of EU, so e to anything, right? I'm not saying make a u substitution, u could be anything, is EU du. Okay, EU du. What does that mean? The derivative of u, right? And it's technically with respect to x, EU du over dx, but that's okay. This is simply used to memorize EU du. That says take the derivative of that exponent and then multiply it by the original exponent. Let's look at an example and make this make better sense, right? EU du. So EU, that means this derivative stays the same, e to the 2x plus 3, multiplied by the derivative of u. So what is the derivative of the exponent with respect to x? So the derivative of 2x is 2, and the derivative of 3 is 0, right? So the derivative of 2x plus 3 is 2. Now, again, I wrote it this way because it kind of flows EU du, but usually we actually write du over dx times e to the u. So, right, this constant usually would move it to the front, 2e to the 2x plus 3. Okay, just, it does look cleaner. However, the formula I gave is, I think, easier to memorize. Now, really quick off to the side, I'm going to write this out a bit more. So what we did is we made u equal to 2x plus 3. Okay. Then we did the derivative of u, du over dx, right, with respect to x is 2. So when I did the derivative here, d over dx, I'm saying the derivative of e to the u, I changed variable to u, and then I apply this formula, right, chain rule. Okay. So therefore this next one, using that same principle, EU, so it stays, and I'm going to go ahead and leave myself room, because I know I'm going to put the derivative here, right? Stays exactly the same. Derivative of e to the any power stays e to any power. But we have to chain rule it and take the derivative of the exponent. Well, the derivative of e to the x is simply e to the x. So e to the x multiplied by e to the x, right? That's weird. It is a weird answer. I mean, it's a weird problem, but really all we can do is remember when you multiply and the bases are the same, right? The bases are both e, then we add the exponents. So we could rewrite this as e to the e to the x plus x. Not that that is much cleaner, but just another way to write that solution. Okay. The next example, it's like, oh man, now we have chain rule, all these e to the x's. I wanted to do this one to point something out. Always check, like, can this thing be simplified first, right? Make the problem easier, and this is going to be especially important in future sections when we look at natural log. Natural log has a lot of properties in which you could reduce the original problem. You could combine terms or expand it, depending on what you need to do. So with that said, I have divided by e to the x. It's one term. If I'm dividing by one term, I could divide each piece by that term, right? So I'm going to rewrite this as e to the x over e to the x. I'm writing it out even though I could have done this in our head. Plus 5e to the 2x over e to the x. Well, this is great here because that's 1, right? Derivative of 1 plus. Now, looking at the second part, when you divide, you subtract the exponents, right? When you divide and they have the same base, they're both e base, you subtract the 2x minus the x. So therefore we get 1x. It's a common mistake to try to like cancel those x's, but remember, division means subtract, just like above when we multiplied it meant add. So we get 5, e to the 2x minus x is just e to the x. And now when we do that derivative, that reduced all the way down to just 5e to the x, right? Really easy derivative. So always check, can I simplify this first? Can I make the problem easier? Quotient rule, it was doable, but quotient rule would have been really ugly on this problem. Okay. In this last example, I wanted to go through a full problem where we're finding the max and min, which means we need to do the derivative, right? And we need to set the derivative equal to 0. So let's look at how that works when we have these e's in the problem. Now, this one gets a little ugly as well because, right, derivative, unfortunately, we have product rule. So let's start with that. We have f is 1 plus x, f prime is 1, g is e to the negative 3x, g prime, eu du, right? Derivative of negative 3x is negative 3, e negative 3x. So the derivative f prime of x is f prime g, 1 times e to the negative 3x, plus fg prime, 1 plus x, multiplied by negative 3e negative 3x. Now remember, we're finding max or min, which means we need to set the derivative equal to 0. But solving this whole thing equal to 0, I don't know, it looks kind of rough. So that's where this whole factoring comes into play. Okay, this term and this term both have an e to the negative 3x. So let's factor that out. What are we left with? Well, here we factored that all out, so we have a 1. And then here we still have this 1 plus x. And then we have this multiplied by negative 3, right? Because we factored the e to the negative 3x out, so we just have negative 3. Okay, we do need to clean this up a bit because I'm going to have to set this equal to 0 and this equal to 0. So distributing negative 3, let's just do this term. We have 1 plus negative 3 minus 3x. And again, we're setting that term equal to 0, right? This equal to 0. And set this equal to 0. Okay. So 1 plus negative 3, that's negative 2 minus 3x equals 0. 3x equals negative 2, so x is negative 2/3. All right. Now, this here, remember, any base raised to any power up here can never be 0. This will never happen. Okay, if I substitute 0, remember e to the 0 is 1. If I substitute a negative, all that does is make it a fraction, right? And in fact, it is a negative. So no matter how we do it, e to any base will never equal 0. In fact, if you think of the graph, right, e to the x does something like this. And then even if I make this negative or whatever, then that's just going to reflect it in different ways. So this e to the negative 3x would actually do, it starts high, right? It reflects across the y. Starts high, ends low. But in either case, it will never cross 0. It's a horizontal asymptote. So we don't even need to worry about that. So x is negative 2/3. Now, though, is it a max or min? Right? We need to check that. We need to verify that. So up to you. If you want to use, if you want to use this method, right, where we pick something on the left and something on the right, test points, see if we get positive and negative, see if it's increasing, decreasing, that's fine. You could also do the second derivative test. I don't know, which one is necessarily going to be easier. Because we have, let's go and rewrite this derivative all factored out. Because we had f prime of x all factored, I think I would rather just do test points. Okay, so that reduced to -2 minus 3x. So remember how this works is I'm going to choose a number over here, like -1 is easy. I'm going to choose a number to the right of it, like 0 looks easy. And we plug that into the derivative, and we check, do we get positive or negative? So if I substitute -1, I would have, first off, this is always positive. So I'm just checking this here. So -3 times -1, right, -2 minus -3 times -1, it's positive 3 minus 2, so positive, which means it's an increasing function to the left of -2/3. If we substitute 0, so this was f of -1, right? If we substitute 0, well, again, this is still positive, but e to the 0 is 1, which is positive. And then -2 minus 0, right? -2 minus 0 is negative. Positive times by negative is a negative. So that's decreasing. If it's increasing, then decreasing, I know that that is a max. So the last thing I didn't really, I guess, write it all out, like find the max or min. Is it a point, or do we just want the x value? I don't know. I guess I should have specified that, but let's go ahead and just plug in -2/3. Right, I know x is -2/3, so f of -2/3 is, go back to the original function, 1 plus -2/3, so 1 minus 2/3 is 1/3. And then e to the -3 times 2/3, right, I'm looking at here, -3 times -2/3 is just positive 2. So the point, if we in fact wanted a point, there's a max at the point -2/3, and then this 1/3 e squared. It's a weird point, but that's right. That's the exact value. That's our point that of this function in which there's a maximum, and we don't have a minimum.